All right, let's get started. Thank you everyone for joining us for 40 Minutes of Competence this evening. My name is Tom Powers, and I will be standing in for Michael in introducing this session. The question on the screen reads, an architect is hired to design a column-free indoor boat showroom with 80-foot spans. Of the options provided below, she should consider blank to support the lightweight roof structure, of the lightweight roof deck, rather. The options are A, cross-laminated timber, CLT, B, glue-laminated timber, glue-lam, or C, laminated strand lumber, LSL. The right answer in this case is option B, glue-laminated timber, or glue-lam. Based on the results of the quiz, it looks like most of you got that right. Each of these three options is a different example of engineered lumber, and that is to line us up for the topic we'll cover tonight. We are joined again by Mario Cortes, who will be, as I understand it, discussing laminated veneer lumber and its structural use cases. Mario, if you're ready, you can take it away.
Okay. It appeared as an innocent case, but there was a house, and it had a hip roof. It has a stud wall with lap siding, and it had a large window that went in one part of it in one corner, and then it had a little bit smaller window that made it into an L. And the idea was that these windows would open up and leave a column-free corner. So the person that was in the kitchen, this house, the kitchen in there, that was cooking, they can look out because this portion of the house was at the very top of a mountain, and there was this beautiful valley beyond it. So what I was tasked to do was to essentially support this corner of this hip roof all in a cantilever portion. And we were using sawn lumber at the time. So what could we use? So above this window, I think you can see my mouse, the cursor. Above there, we're going to have a beam that cantilevered and supported the corner of the hip roof. So what to use? We didn't want to use a flitch beam. That's old construction, so that was using sawn lumber with steel plates that are sandwiched between it, because it requires a lot of times a different trade, a trade that can bore through steel plates and carriage bolt it all together to sandwich that header beam that needs to go up above the window. So I started looking, and what we came up that was available in this part of the country was, let's put an LVL. LVLs, so let me back up. So this ended up being the cases that I was confronted with. Okay, so just to make the mathematics somewhat simple, you have a beam, and then I put a uniform load on there. It's actually a triangular load that is decreasing towards the free end, which is on the left. And then the point load of the hip rafter, the hip beam coming in and putting a force at the very end of the cantilever. Okay, so both cases, you have a maximum moment at the very end, at the face of the connection, the support. If it's a point load, it's a triangular moment. If it's a uniform load, it's a parabolic moment. But the critical moment is always at the end, at the support. At the free end, that's where you have the maximum deflection. So I started to make the calculations to come up with a cross section. So LVLs come in and sizes that are sawn lumber that are used for joist. So 2-by construction. So how many did I need to gang together to make a large enough beam to support these forces and also control the deflection at the free end? So seemed reasonable and not hard to do. This span over the large portion of the window, this was a 10-foot span. And this other one, the smaller window that makes an L at the corner, that one was 5 foot long. We couldn't make it too deep because it would infringe on line of sights. And then what happened was, okay, I did the calculations. Structure came in contrast, or you had to at the same time know about construction, because as you can see, the deflection, the beam deflects downwards, and so it would crush the glass that's underneath it. So I was in class giving a lecture, and I get a desperate call out on the job site that the beam had deflected too much that they could not put the window underneath it. I said, impossible. And that's because when I was doing the calculations, I had put an impact load. So I had doubled the loads, the normal gravity loads on here, and made the deflection, the maximum deflection for this beam, instead of L over 240, I think I made it L over 1,000. So I was purposely coming up with a combination that the deflection would be so small that it would not interfere or destroy the window. So what had happened? Let me share another. So LVLs. So LVLs are these laminated beams. They're essentially a really thick plywood. And so the layers are placed vertically on here, not horizontal like a standard glue lamp. And the glue joint is also vertical. And they can span long distances, and they are very strong. There's all sorts of tables. They also have the ones that that the contractor ended up ordering had a camber, so they have a slight haunch on it. And that's what caused all sorts of problems out on the job site. They come with a haunch, and when they're supported at the ends, so if there was a support at the end where back to this image. So if there's a column at this end and a support at this other end of it, they come already with a haunch on it, so they have curvature to it. So out on the job site, the project manager, lead contractor said, haunch up. So if you're putting an LVL, you want to make sure that the high side goes up and the curve down at the bottom will come, the whole system will come to level when the dead load is actually applied to the LVL. Well, when it comes with a haunch up, In a cantilever case, it actually takes the shape of this deflected beam that I have on the screen. And the deflection was not due to the loads or the engineering, it was due to how the LVL came to the job site. So the solution out on the job site that made me cringe was to get it so that it was more level. They just cut the bottom. So they took a chalk line, strung it across the LVLs, and then took a saw and cut them. Absolutely the wrong thing to do. The proper thing to do in a case like this was to remove how they were put into the wall and turn them upside down. So if I start to cut the bottom of this and remove the material below it, I'm taking strength out of the moment of inertia. So with a smaller moment of inertia, what will happen is the deflection will increase and keep increasing. The more cuts I make, the weaker beam that I'm making. So that was something I had to contend with in this case. But I knew I had put extra forces, so the safety factor that I was using was considerably higher than would actually occur out at the job site, or especially when the beam was not loaded. Another issue with LVLs is that they can be fabricated to be considerably longer than sawn lumber. So the LVL that went over the large cantilever at this point, I wanted a backup length equal to the window, the cantilever. And we actually ended up bringing out to the job site LVLs that were 25 feet in length. So that was half of the span. I'm sorry, half of the length of the wall at this point. And that's so that to make a rigid connection at the end in timber is extremely hard. If I would have put, for example, a 12-foot length, I don't know the connection that you can make at this right-hand side of the beam that would be rigid enough and not deflect or actually lever out of place, out of level. So when a big LVL shows out on the job site, they're coming on the flatbed of a truck, 25 feet in length, and they come flatwise. So another concern with the case that I was at was to make sure that the construction team actually knew how to move them around. So first thing in order there is you have to put it on edge to move it. Otherwise, you snap it. So those are issues with the new engineered lumbers, that the lengths can be much greater than sawn lumber. And so you have to be concerned in how to use them in construction. The nice thing about them is that they're extremely strong, and a carpenter out on the job site has all the tools to be able to use them and cut them and shape them if they need to, when they're so narrow. So these were 1.5 inches in width. So they matched up with sawn lumber 2x construction. You have to make sure that when they go in and are put in place, that they do not twist and lay flatwise, because they can make the piece narrow and deep, But if you don't have a way of bracing it, in this case, they were glued and screwed together so that they ended up, the cross section in one dimension was 1.5 times 3, 4.5 inches in width by 14 inches in depth. So that cross section doesn't require any additional cross bracing. It is stable enough that it will stay vertical the way that I've drawn it on the screen. I will share another one. So after the call, while I was lecturing and going to my office, and I became a little bit gun shy at using or doing cantilevers. But then I had another opportunity to do another cantilever case, which I'll show you next. A masonry building right here in Blacksburg. It's at the end, at the intersection between Main Street and Price's Fort. And it's this corner right there. It cantilevers out 10 feet. It has a steel structure behind it. So this is brick veneer on metal studs. So you can see, if you look carefully enough, that there are these control joints that are placed right around the windows. So there's one there. There's another one here. So now what was an issue was that this is a big dead load. Masonry is heavy. Once again, this corner can't deflect, because if it deflects, this masonry starts to open up and crack. Right? If this bends down. So I had to specify in here rigid connections at all the beams and column connections, so that all segments of the W shapes that are in back of here, supporting the roof, supporting floors, every segment of it. So all the flanges and the webs are essentially go through, are continuous. And the column then is welded, in this case, bolted together to make rigid connections. So then it doesn't become as significant. The 10-foot span to something that is at least 30 feet deep is not as significant for the 10-foot span, but any deflection would still make the masonry open up, and we couldn't have that over the entire life of the building. So this building, I think right now, is close to 15 years old, and no cracks are in here, so I'm still in Blacksburg. The joke with my wife was, if this started to crack, we would move away from here so that somebody else would get in trouble and we would be in a different state. So cantilevers are critical designs because at the end that is supported, you need to have that rigidity that will allow the cantilever to span. And at the free end, so at the end of the cantilever, you always are dealing with deflections that may be significant. So I have two more things that I can show you that might be of interest. So these are much greater, more important buildings. So this is Richard's Medical Center. One cantilever case that I know in concrete. So if you look carefully at these corners, these are, the cantilever is expressed in steps. So when it comes out of the concrete support, it is deep, and then it thins down towards the end, and it has windows placed underneath it. This is to let daylight come into the labs medical labs that are underneath it. Let's see which other ones. This is incredible. The first time that I saw it. So we did a study both in cantilever and suspension. So this is a bank. It's Standard Bank in Johannesburg, South Africa. And so this is a tower. It has these giant concrete brackets that straddle 4 cores, concrete cores. At the end of these brackets, there's a concrete hanger that goes down. And that was the first thing that struck my eye. How can there be concrete hangers? Because I know the hanger has to be in tension. So hangers are dropped, and the square plan is picked up by these concrete hangers that transfer the weight of 13 floors to the end of the cantilevers. And then these large brackets send it to the 4 cores at the center, and the cores bring it down to the ground. Again, a case of, in here, tension and cantilever combined to bring down the weight of this building down to the ground. Now, this is a passion that I have. I don't know how many of you know, but I do a lot of fly fishing. And I make bamboo fly rods. So I make these rods. They have, the cross section is a perfect hexagon. So I have to take 6 strips of bamboos that I shave to a specific dimension, glue them together to make the blank for the rod. And so when my wife was pregnant with my son, I had a person that introduced me to fly fishing. He said, this is the true way of actually going out and fishing. So I had no equipment whatsoever. So he said, well, you need to go buy a rod. And we headed to Orvis in Roanoke. Orvis makes cane fly rods. On the way there, we stopped at another store that had fiberglass rods, and an elderly gentleman came up to me and my wife and said, so do you know a lot about fly fishing? You said, no. He goes, well, you grab the rod and you shake it. And if it bends a lot, you say, good action. That's all you need to know. So with that amount of knowledge and information, we went to Orvis in Roanoke. For some reason, my wife went to where all the rods are displayed, and she grabbed a cane rod, shook it, the thing sprung to action. So we said, good action, good action. Then our eyes went to the price, and I just about fainted that a fishing rod could cost something like what you see on the screen in here. So I came back to Blacksburg. There used to be a bookstore in downtown Blacksburg that was called Book Strings and Things. And I had looked through the shelves, and there was one book, How to Build Your Own Bamboo Fly Rod. Well, I went there. I went from Roanoke back to Blacksburg, bought that book, and that evening started to read it. So now I make my own bamboo fly rods. And I will share yet another screen. So I would give a lecture to the thesis group each year about how all the calculations that I made for designing my own bamboo fly rods. And so at this point up here, I have properties, so weights of bamboo, how to convert it to ounces, moment of inertia because what I am bending is a hexagon made out of 6 strips of bamboo. And then I began to make the calculations. So this is all a spreadsheet. I'm calculating moments of a cantilever every 5 inches along the entire length. So this is for a 7-foot long fly rod. The weight of the bamboo itself, the weight of the varnish, and the guides, the weight of the ferrule, so that metal piece that connects each segment of the rod. Then at the end, I total up and then calculate the dimensions for each hexagon every 5 feet. So, I'm sorry, every 5 inches. So, how deep do I have to make it? The hexagon at each point. Okay, so that is, so I end up with a table like this that gives me how deep this hexagon needs to be. And each one of the dimensions for a specific depth at each one of the points. And so these are all cantilevers. I'm sorry, let me do one more thing. So this is an amazing cantilever. So a cantilever building that Jean Nouvel designed in Switzerland that comes down to a single line. So when you look at it, it has this very thin profile. And you don't really see how he did it. So from across the bay at this point, the lake, all you see is this edge. It's large enough that underneath it, they put a carnival underneath. So a Ferris wheel, merry-go-round, and all sorts of booths underneath this one. This dramatic cantilever in Lucerne. I was lucky enough 2 years ago when I was in Switzerland that I went and visited and rode the Ferris wheel right underneath it. This one has begun to become, other architects are copying it or using similar design. So there is another. So this one, you can see how they actually did it. There's this giant metal truss, but it also ends in a single line. The profile at this portion of it is so thin. That's in order to make a covered entry plaza to this convention center for the university where the Rolex Center is at. And this is also the building that kind of receives you if you come in the train to the EPFL. So those are some new existing cantilevers that are much larger than what I did, but you can see some of the strength of using cantilevers for certain conditions. This one is something that in North Carolina, in Charlotte, Mario Boda backed off. So they wanted to do a giant hovering roof for a public space for the Beckler Museum. And they ended up succumbing, and they put a big hollow brick column in the middle of that space. So that's it.
Yes, we've gotten a couple of questions about the LVLs, the main topic.
Yeah.
Is there a maximum cantilever on LVLs from a practical perspective?
Hmm. I would not go any further than what I used. I would try to keep it at kind of light wood standard dimensions, 8 feet. Now spans between supports, not cantilever, they can go probably in the range of a long joist span. So they can easily go 20.
And in the project that you're referencing, was there also an LVL over the 5-foot window, the shorter leg of the
Yes.
L?
Yes, but that was just safety. So the LVL in there did not have to be as big or as many laminates. But in order to support a little bit the end of the 10-foot cantilever, that smaller span could actually act a little bit as a support. But as the way they constructed it, they put the large cantilever first. And then the project came to a halt because they had put camber up and it looked like the cantilever was deflecting. I mean, we had the warehouser comes out, the engineer, the warehouser come out to see what was going on. We got the job manager to make sure that he understood what was happening. And so there was a lot of back and forth. The engineer from Warehouser said, no, everything was correct. They just had installed it incorrectly.
All right. I think that brings us to the end of the questions I've seen. Mario, thank you for your time. And everyone else, good night. Get licensed.
All right. Thanks.